Good morning, good afternoon, whatever time zone you're in, and welcome to this session on ocean observation and sensing. It should be probably the third that you're going to see in the Oceanology conference this year. We have two speakers in this session. But first, my name is Gus Jeans, and I'm chairing this session. The first speaker is Martin Amis, who's a systems engineer with Ifremer. So please, Martin, take it away.
Okay. Okay, could you see the presentation?
Yes, that's good, thank you.
Okay, thank you. Good morning, Chair. Good morning, ladies and gentlemen. My name is Martin Amis. I work for Ifremer, which is the French Research Institute for the Sea. And today I'm going to talk about the three-headed deep harbor, which is a reference for CTD comparison. So this project has taken place because there is mainly one CTD supplier today for the Argo network, and we believe it could be something very bad if something happened to Seabird or their CTDs. So we developed a platform to test other CTD in order to qualify and diversify CTD available for the network. Okay, so I've divided my talk in 4 parts. I will give a brief overview of what the Argo program is aiming, as to what the deep harbor is. Then I will talk about the three-headed deep harbor, and then I will give a conclusion, little perspectives about the project and what could follow. So let's start with the Argo program. So Argo is a global in-situ observation system designed to record CTD profiles during ascent of a profiling float. The project is mainly used for climate change research, oceanic mass mechanism, as well as interaction between sea and atmosphere. There are about 30 countries who work on it. All the data is open, and today there are close to 4,000 profiling floats all around the planet. So the data for the core Argo is recorded up to 2,000 meters. I will now talk about what is a profiling float. So basically, a profiling float, it's a fully autonomous buoy which records CTD data during ascent. All the data is transmitted by a satellite. On the float, it's at the surface. On the right side of the slide, you have a typical cycle for a float. So basically, the float will descend to a predetermined depth of 1,000 meters. Then it will drift during 10 days, descend once again to a depth of 2,000 meters. And then during the ascent of the float, you have the salinity and the temperature, which are recorded. So that's what the float will do over all its lifetime. And once again, once the float reaches the surface, data will be transmitted again. Before talking of the three-headed deep harbor, the three-headed shared family components with the deep harbor ones. So I would like to give some characteristic of this float first. And I will start with a little bit of context. So over the last decade, requirements for scientists evolve. They do want more data about deeper water masses, at least from 4,000 meters. So we had to develop an equipment which is able to reach such a depth. Sorry. So this is a deep harbor on the left of the slide. It is equipped with an SB41CP CTD from the American company Seabird. Originally, these CTDs were designed to cope a depth of 2,000 meters, but then Seabird qualified it to reach 4,000 meters. The float weighs 26 kilograms and is able to do up to 200 spot sampling cycles and up to 150 cycles with continuous pumping. It was commissioned at sea in 2015 and then manufactured in 2016. There are about 50 deep harbor all around the planet, and at Ifremer we plan to deploy 50 more over the next 2 years. So we like to say that the deep harbor has a high payload capacity because it's designed around the tube, so it's easy to embed more equipment or sensor with few mechanical adjustments. And because of that, as well as its robustness, as its high reliability, we developed the three-headed from the deep harbor. And today we say that the deep harbor could be considered as a reference test bench for future design. And if you took a look at the right side of the slide, you have an example of a previous project, which is called the Deep Harbor Wapiti, which is equipped with a DCP at the bottom of the float. Now I'm gonna talk about the three-headed deep harbor. And I will start once again with a little bit of context. So as I said during the first slide, there is mainly one supplier for all the profiling floats, which is Seabird with his SB41 and SB61 CTDs. And today the community is now ready to diversify sensors available for the core Argo network. But before deploying a new profiling float with a new CTD, they obviously need to evaluate and qualify new CTD. So we have focused our choice on the RBR Concerto 3, which is able to reach 4,000 meters deep. And why we call it three-headed? That's because we also add the SB61 on the deep harbor, because this is a unique occasion to compare the two CTDs from Seabird side by side on the same platform. So that is the context, and now I will give some brief characteristics of the deep harbor, three-headed deep harbor. So it is also able to reach a depth of 4,000 meters. It is able to sound up to 1,000 CTD triplets per cycle. It will last up to 90 cycles, and all the data is compared in situ. And this is a look this slide shows what are the mechanical aspects of the floats. So basically, we have to add two synthetic forms and a new ballast to adjust buoyancy, as well as HDP collars to maintain the floats. You have the SB41 here on the float, and side by side you will have the SB61 here and the RBR Concerto here. We chose to align the CTDs on the SB41 here, but we have differences between the positions of the sensors. So temperature sensors are fine; they are all at the same level, but conductivity cells sensor will be a slight below the RBR ones for the seabird ones. And there is a difference between the pressure sensors, but all those differences are well calibrated to avoid any discrepancies in the data processing. We also took a close look about synchronization process. I will talk about it a bit later. We chose to work with two PCB. So you have the first one, which is dedicated for to command the movement of the profiling float in the water column, to store the data, and then to command the satellite transmission. So that's basically for the core Argo mission. And then you have a second board, which is an acquisition board. That second board is dedicated to the acquisition process. So this second board will power and communicate with the added sensors, added CTDs. And we spend some time to make sure that there is a good synchronization process in order to have a correct timestamp between the CTDs. So you have samples recorded every 2 seconds, and we can guarantee there is a time accuracy between CTDs below 0.3 seconds. If we take a look of the software aspects, so there are 5 configurable slices that will allow the user to be able to choose to oversample up to 0.2 meters for a dedicated thickness of the water column. On that slide, on the left side, that's what we plan to do for the first profiles of the 2 prototypes. So basically, there will be an oversampling between 50 and 90 meters, because where we plan to deploy the floats, there were previously a deep harbor on the same area, and it recorded, for example, high gradients of salinity on that thickness. But the user is able to change over all the lifetime of the float those parameters. So we will be able to oversample other area. Now I will give a brief overview of the status of the project. So the first prototype of 3-headed deep harbor was qualified at sea in the Mediterranean Sea in 2018 and 2019. It was basically to make sure that all technical aspects of the float are working well, such as a synchronization process, software management, etc. And there will be a campaign during the month of December where we plan to deploy the 2 prototypes in the Canary Basin. So we finally decided to deploy the two floats in the same area because that will give us even more data to intercompare. And this is a zone where we have already a lot of profiles from previous deep floats. That's an example of what kind of data we acquired during the qualifications. So we did 5 cycles. The float did 5 cycles, and 3 of them reached 2,000 meter deep. Sorry. That was enough for us to validate the technical aspects, and we were already able to see a slight difference between the salinity measurements from the RBR1 and the seabirds from CTD. Sorry. At this time of the qualifications, RBR told us that the last salinity equation was not fully ready on the CTD. But for the 2 prototypes we will deploy, the RBR CTDs should have the last corrected salinity equation. So no, it should be fine. And it's time to conclude. So what we would like to show on this talk is that the deep harbor shows a good reliability, a good payload capacity. So it's easy for us to embed other kind of sensors. And for this project, we developed the 3-headed deep harbor for in situ CTD intercomparison. And we hope that will allow the Argo community to be able to say if we can now have a new CTD for the core Argo. And I would like to say also that at IFROMER we have a strong partnership with the NKE instrumentation, and as well as the LOV. NKE is our partnership for industrial matters, and Villefranche, the LOV is working on biogeochemical floats. So we are today thinking to make a deep harbor BGC because we have skills in both BGC and deep profiling floats. And that's a slide I added at the last time because that's work we have done this year. It was to implement the RBR Argo 3 CTD on the harbor floats. So to reach those floats will be able to reach 2,000 meter deeps. And we also plan to deploy 2 of those prototypes during the same campaign than the 3-headed ones. Thank you for your attention, and don't hesitate if you have any questions.
Thank you. Quite often if I clap, the audience will begin to clap as well. So hopefully they're doing that somewhere now. So thank you very much.
Thank you.
There's no way of us to know yet. So yeah, thank you. You've kept to time very well. An interesting presentation. I can ask a few questions, but before I do, are there any questions from the other speaker or maybe the organizers?
Okay.
Or shall I just ask the questions I have?
I think you should ask.
Yeah, I think I'll ask my questions.
Yeah.
Okay. So you on your slide 15, it might be good to go to slide 15.
Yeah.
You have the configurable slices.
Yeah.
And I think I understand you fix the depth ranges of these in advance.
Yes.
Okay, because obviously if you're going into the open ocean, you have to anticipate drifting into other regions. So are there plans to make these adaptive? So
yes, the profiling floats, you can reconfigure profiling floats once they are at sea. by a remote control. So this configuration is for the first profiles, but it will be changed over the life of the float. So we will be able to adjust what kind of profile we want.
And that can be done in the as soon as they surface again.
Exactly, that's it.
Okay, good.
Before starting a new cycle, you will have new parameters or not, and these parameters will be taken by the float, and then the float will start a new cycle.
Excellent, thank you. 2 more slides down, you have the temperature and salinity profiles. I zoomed into your slides in advance, so I could see that the 2 seabird sensors, the 41 and the 61, are actually right over each other for salinity, and it's the RBR sensor which is noticeably higher in salinity. So it's probably worth highlighting that. So what implications does that have, do you feel, in terms of the point you made at the beginning of your talk, that it will be good to have alternative sensors from seabird? That, without getting commercial, of course. It does this. Well, I'll ask you for your thoughts on the technical side of that.
That's more metrological aspect for me, so than the technical aspects. What we would like with these instruments is to check if the RBR CTD could be compliant with the Argo network. That's mainly the goal. For the 2,000 meter deep CTDs from RBR, as far as I know, it's fine. But for deeper ones, such as the one we used during those qualification, it seems to have a slight difference. We asked RBR about these drifts. They only told us it's because the last salinity equation is not fully ready. But no, it should be fine. And if it's not the case, that will be the scientists which will tell if we can add this CTD or not on the float.
Yeah, but it's well established that the Seabird 61 is the benchmark widely
exactly
accepted.
So all data, even the SB41 data, will be compared from the SB61. We consider the SB61 as a reference.
Yeah, so it may be that some further calibrations required under certain conditions. Okay, probably time for another question. You mentioned the biogeochemical sensors. What sort of parameters can you measure on these in an automated way?
It could be chlorophyll, it could be, I don't know exactly the sensor used by the LOV at Villefranche, but I think it could be any kind of sensors. But as far as I know, for BGC profiling floats, there is not a lot of sensors available for each characteristics.
It's a rapidly emerging area. I wondered what was already possible. Okay. Are there any other questions from anyone else who's listening in? Or if not, I think those were my main questions. I guess not. Okay, so thank you again very much, Martin. And if you want to ask a question to our next speaker, you'll be very welcome.
I will.
But if not, I'll do so. So thanks again, and the audience will clap with you. So okay, thank you very
much.
Thank you. So our next speaker in this session is João Sousa, professor in the University of Porto in Portugal. So please take it away. And I can see your screen well.
Good morning. Then again, thanks very much for the intro. So I'll be talking about exploring the Northern Pacific subtropical front with the coordinated ship robotic surveys. But first, I'll say a few words about our lab at Port University. So in our lab, we've been designing, building, and deploying autonomous underwater surface and air vehicles for networked operations. Applications include oceanography, marine biology, security, and defense. And we've also been developing the software that enables all of these guys to work together as teams. And this is our vision for a sustained presence in the ocean. So you'll have lots of different assets, lots of different types of interactions, interoperated communication links above and underwater, sensing links, mixed initiative interactions, meaning operators in the planning and control loops. Vehicles will come and go, same thing with the operators. There's the issue of scalability. Right now we know how to operate, let's say, 10 vehicles at a time. What about 100? What about 1,000? Then we also want to use vehicles as data mules when you don't have permanent connectivity between two nodes. There's the issue of distributed computations. There's also the idea of having vehicles capable of launching and recovering other vehicles. But in the end, in our vision, we would like to treat this ensemble of assets as a system that has properties that are a function of the vehicles, a function of the communication networks, and a function of the interactions that you establish over these. So we want the system to have organization-like properties. One observation, this is not PowerPoint engineering, so we've been developing the tools and technologies that will enable us to achieve this vision. And we've also been testing all of these systems at sea, as we'll see next. First of all, our vehicle systems, we have lots of different toys with different types of toys, modular, low cost, some of them long endurance. Important thing is that they share the same software and they reuse most of the computational hardware, and they are interoperable, meaning that they can talk to each other. This is our workhorse, the LAUV, which was designed in our lab, now there's a spin-off. And so two versions, upper water column, endurance 50 hour plus, and mapping. And you see here the vehicle in action. Very simple to operate. You just need to make sure that there's water there. And then again, software is very important for what we do, as we'll get to see next. So we have an open source software toolchain, which is in use in over 20 countries. So you have Dune running on board. You have IMC, which is our protocol for communications. So all nodes in the network talk IMC. And then you have NAPTES, which is basically the command and control framework that will run on your laptop. We operate a lot in terms of op areas. We've been in lots of different places. We've been organizing large-scale exercises. We have deployments from shore, from ships, and from also manned submarines. And we have over 100 days of operations per year. In 2018, our UVs did over 4,000 kilometers underwater, and we had over 200 flights. Then again, talking about operations, something that is very important is we've been organizing the Rapid Environmental Picture exercise in cooperation with the Portuguese Navy and CMRE since 2010. There are several focus areas, and this is an invitation-only exercise. Some pictures. So as you see, it's quite diverse, and some figures from the 2019 edition. So basically 2 weeks, 7 navies, over 10 companies, over 800 people, 9 ships, including 1 frigate from the US that swung by with some material there, and 1 manned submarine, and over 50 AUVs, ASVs, and UAVs. Okay, so this is basically what we do in our lab at Port University, and as part of our experimental planning, our deployments, We basically led the exploring fronts with multiple robots, which was a SOI cruise funded by the Schmidt Ocean Institute. So we deployed from the RV Falcor. You see a picture here. This is my team. So we had people from Port University, from Algarve University, from NTNU in Norway, from the University Polytechnic of Cartagena, from Harvard University and from the University of Rhode Island. And we also had collaborators and people working with us in preparation for the cruise, people from the Portuguese Navy, from NASA Ames, from SINTEF, which provided very important support to what we did. Okay, now a few words about the cruise. So the goal of the cruise was to demonstrate a novel multi-vehicle system capable of finding, tracking, and sampling features of the ocean with adaptive spatial and temporal resolution. And here's a video.
During this expedition, our team has created a system to conduct oceanographic surveys with unprecedented levels of detail and scale. Approximately 1,000 miles off the coast of Southern California, we are studying the subtropical front. Here, two masses of water collide, which generate a unique mix of physical, chemical, and biological features. Before the expedition, autonomous vessels helped us determine the approximate location of the front. When we arrived here, we deployed CTDs to gain a more precise understanding of its spatial dynamics. Our autonomous underwater vehicles, which were specifically designed for this expedition, can cover hundreds of kilometers and stay in the water for up to 50 hours. They travel in a yo-yo pattern, sending real-time data back to the ship every time they surface. Our fixed-wing vertical takeoff UAVs can fly faster and further than quadcopters and carry a variety of sensors. The data our autonomous vehicles collect helps us locate biological hotspots where we conduct more detailed sampling.
We are deploying very advanced technology that needs to be refined through experimentation. And by doing that, we hope to establish some of the foundations for the future of oceanographic surveys.
Okay, and now a few words about the North Pacific subtropical front. It's located here. Let's say basically you see this red ellipse, and it's a sharp boundary where cold fresh waters from the north meet warm salty waters from south. It's very strong in salinity. There's a very strong salinity signature, but a weak sea surface temperature signature, meaning it's very difficult to see from space. It's located approximately 1,000 nautical miles west of San Diego. And in this picture, you see these are tracks of previous ship tracks from previous studies. And these were the assets that we deployed in this cruise, in addition to the Falcor. So we had 3 VTOL UAVs, so we had quadcopters, we had 1 wave glider, 2 sail drones, 7 AUVs. And in addition to our software toolchain that I already mentioned before, Dune, IMC, and Neptus, we also had Ripples, which is basically a communications hub for data dissemination and situation awareness. So duration of the cruise, 3 weeks, and we were on site for 2 weeks. So basically we had a web-based mission control center. So we are operating non-stop 4 shifts per day. We had operators in Porto, Portugal, and on board the RV Falcor. So this was mission control center. This is what you would see in Porto with a planning view, a timeline view, risk analysis view, and data view. And you also had the mission control center on board the Falcor. And of course, we were using SATCOMs. So our AUVs did over 2,000 kilometers and the ASVs did over 10,000 kilometers in this cruise. The question then was how to find, track, and sample the front. So basically we came up with task templates. There's one. I'll show a few examples. Very simple, yo-yo. Task 5, which is a kind of a front tracking, basically zigzag pattern along the front. Task type 8, multiple AUVs performing single file radiators, but synchronously. And now let me talk about what we did in the cruise. First task, finding the front. Why? Because it's very difficult to see from space. 2 reasons. There's a very weak temperature signature, and it's mostly cloudy there, as we could tell. So basically what we did was we sent one wave glider and 2 sail drones that were deployed into the target area ahead of the ship's arrival. And then we were looking at sharp transitions of temperature and salinity, basically to try to figure out where the front was. Basically, we were ingesting this data. We're also ingesting HPC run model outputs and data also from Argos floats in the area. And what you see here in this panel here are tracks of the sail drones and of the wave glider and locations of the Argos floats. These were color-coded by salinity. So based on some of these observations, we selected this area for the initial survey. There's more to it, but for the moment, let's just say this. Then what about planning for coordinated ships robotic surveys? So basically we had a representation here of a track from a wave glider and a track from a sail drone. Based on these, we could tell that the front was located somewhere in between. And based on this, we picked this rectangle for the op area, 165 kilometers by 95 kilometers. At the time, the Falcor was still far away. Then Falcor moved to the nearest point in the op area and performed the north-south CTD survey. While we were doing this, we also had AUVs performing mowing lawn pattern survey along the same area. The Falcor was also tracking the AUVs and performing CTD casts. And we kept doing this up until we covered the whole rectangle. So this took several days. Based on these observations, we were able to come up with a very good understanding of what was going on. And based on this, we decided to deploy short-range AUVs along the front with other sensors. We also decided to fly a VTOL UAV for aerial surveys with a DMS sensor that measures concentrations of DMS gas and a multispectral camera. And finally, the RV Falcor also performed CTD casts along the front for biological and biogeochemical characterization. And this kind of tells you what we know now about what we saw. In the background, you see the only SST image that we got from the area. Below here, so kind of down here in this kind of sort of red area, this is basically the front. And then there was a filament that was detaching from the front. This was a big filament, so the cross track is something like 20 kilometers. And the other interesting thing is that we saw and we measured currents of up to 2 knots in this area here. So superimposed on this, we have AUV tracks also color-coded by salinity. And then you see that there's an interesting correlation. Of course, you have to keep in mind that time, let's say, accounts for some discrepancies here. So this is kind of a 3D view of the front with measurements taken by the AUVs. As I mentioned before, we also performed flights with a DMS sensor provided by NASA Ames. This is a prototype, and we were measuring concentrations of DMS gas along the front because the idea is that DMS is a proxy for biological activity, and that's what we did. We also had AUVs, so performing other types of tasks, namely automated front detection and tracking. First, we tested this with Wave Glider, then with the Falcor, and finally with the AUVs. And you see some tracks here. Then again, color-coded by salinity. And we also performed high resolution coordinated sampling using AUVs coordinated with the Falcor and UAVs. So basically these guys were moving information and collecting data in an area, in this area. In terms of data analysis, and then again, I want to go into lots of details. So we had SSD data, not much, but we also had measurements from the AUV and from the Falcor. And we also used data from remote sensing, namely finite size Lyapunov exponents. And what you see here in this picture are tracks of the AUVs, color-coded again by salinity. Then these red arrows basically give you a sense for currents in the area. And in the background, you see a finite size Lyapunov exponents. And then again, there was a very interesting correlation between what you measured in situ and what was given by remote sensing data. In this case, finite size Lyapunov exponents that give you sort of the structure or the skeleton of the flow. The same thing with the SST data. So we were quite happy with what we achieved. We are still working on all the data. And now, finally, a few words about future oceanographic field operations. So let's hear what he has to say.
So we take all these different systems that go beyond the footprint of what a ship can do. They can be 20 miles this way, 20 miles that way, and help us understand the oceans a lot better than we do now.
So this is exactly what we did. So the footprint for what we were doing was big. So because our operation area was pretty big, as you could tell. So a quote from Eric Schmidt, technology first, new technology should drive the SLI science program. So basically we were quite happy with what we achieved. This was an interdisciplinary team. So we had people from engineering, people from computer science, marine biologists, physical oceanographers, chemical oceanographers, and we were really happy with what we achieved. So in summary, we successfully demonstrated a novel approach to observe the ocean with persistent network ecosystems. The front was located precisely as predicted. The easternmost segment of the front was studied in unprecedented detail. And for the first time ever, a mesoscale filament of a major open ocean front was mapped with submesoscale resolution using largely multiple AUVs. Operations, so AUVs did over 600 hours, over 1,000 nautical miles. The UAVs, so we ran operations with IR, multispectral, and EMS gas sensor. The UAV also worked as a communications relay for bent light and offsite communications with the AUVs, flight time up to 55 minutes. The mission control center, so we operated non-stop for 2 weeks on site because we also had 2.5 days for transit time each way. So 4 daily shifts, 2 operators by shift. This is very important. And we also performed coordinated ship robotic surveys. Finally, and as kind of a main conclusion, the systems and technologies demonstrated in this cruise are applicable to other frontal regions as well as to other phenomena of the world ocean. And this is pretty much what I had to say. So thanks very much.
Hey, thank you. I've set a precedent now of clapping, even though the audience is not with us yet. So it would be rude if I didn't do this now as well. So yeah, thank you, Joao. You've done a great job of getting through a lot of material in good time. So I can ask a few questions. I'll ask if maybe Martin wants to do so first.
Yeah, okay. I was wondering, your robots seems to be easy to deploy them, but how do you manage to recover them during a campaign like that?
Yeah, that's a good question. So we were planning to do that with a kind of a small crane, but in the end, and because the conditions were quite decent, we put a rib in the water and we were just recovering them by hand.
Okay, thank you.
Okay, that's a good question. Thank you. I have a question. Could you go back to, I think it's maybe your slide, well, actually, any slide will do. Slide 13, where you had the summary of the instrumentation. So a bit further.
Yeah, I think I know.
Yeah, maybe I should, yeah, go back a couple more.
One?
Yeah, so there's a lot of physical oceanographic instrumentation there, but there's no, are there any direct measurements of current? Because later you talked about the currents you detected being 2 knots in the region of the filament. I'm wondering how you get the current, the surface current and subsurface current information.
That's a good question. So we got that with the ADCP that was mounted on the Falcor.
Okay, great. And then if a few slides forward then. Actually, yeah, maybe just 2 slides forward initially. Yeah, one more. So here you have yeah, one up. Yeah, so here you have the sort of vertical track of the autonomous underwater vehicle, and I'm wondering if you've looked at, if you have sort of, you know, fairly strong currents in the area of around 1 meters per second, and presumably these, well, I guess the question for you is, do these vary strongly across the front? Are the currents themselves due to the front or the filament, or are they background currents that are advecting the whole system? And also, how do they vary through the vertical? Do you have a feeling for that?
Yeah, so basically, I can go to this slide here. So we measured these kind of very strong currents in this region, in the filament that was detaching from the front. And here was a bit tough for the UVs to operate here because of these currents. But still, this is a good example in which AUVs could basically complement what is being done or what can be done with gliders. Why? Because we have more control of speed, so we could go faster if there was a need to. So our AUVs, of course, in terms of power consumption, you pay a price, but they can top 4 knots. The nominal speed here was 2 knots, but this is what we did. In other regions, currents were not as strong as in this region here. Mm-hmm. And then again, in vertical profiles, you could also see variation. So you could see currents going one way, and let's say kind of tens of meters below, currents going the other way. So this was very kind of initially this was puzzling to us, because this is our initial up area, and then we thought, hey, we found the front. And this is also another important lesson from the cruise, which is combining lots of different assets, putting assets in the water, for example, here, leaving them there, and then moving south with the Falcor, which can move much faster, so that you can get a kind of a better understanding of what was going on there. So because initially we thought, hey, this is the front. Then we went south, okay, and this is exactly what you saw, okay, a kind of high salinity, and then a kind of low salinity and high salinity again. So this kind of looked crazy. And then it was then that we decided, okay, hey, let's go for this kind of a sort of a mesoscale mapping with unprecedented submesoscale resolution.
Thanks, detailed answer. I guess there's a challenge still to get these autonomous platforms, whether they're propelled or gliding, to provide the best data during currents that are varying spatially, vertically and horizontally. And a related question is, maybe if you go up a couple of slides, or it's not necessary, this slide's good. You were explaining how you designed the survey. So it would have taken some time to complete that map. So if the feature itself has to be moving relatively slowly relative to your sample, have you got a feeling for how well that condition was met for this survey?
Yeah,
because there's currents within the filament, but is the position of the filament moving while you're surveying it to a large degree?
Yes, so it was, let's say, it wasn't moving much, but you could tell from the, let's say, some of the initial surveys, because between the first survey, let's say, putting AUVs in water, starting this kind of a mesoscale mapping, and getting them out of the water. So after covering the whole rectangle, I think that we had something like 5 days. So we were seeing some evolution in this filament.
Okay, good. I guess I have to ask because I don't know if you know, you had a slide courtesy of Jose da Silva, who I worked with, and my PhD was internal waves. So I have to ask a question about internal waves. Have you had an experience of deploying these sort of systems within the very rapid changes in currents and density structure within internal waves? And what's your views on how effective they would be?
Not here. Not in this region, but we've been exactly working with José, working in southern Portugal in a place in which we were kind of basically trying to figure out what was going on, because we think that there's a mechanism for the creation of internal waves there, and so we deployed AUVs there, so trying to figure out what is going on, but results were inconclusive, meaning that we would like to go back and get a better understanding of what can be done. So we'd also like to complement that, let's say, not only having measurements from AUVs, these kind of very simple AUVs, but AUVs also with ADCPs, so that then you can also get the kind of current profiles and see that. So say, trying to be very succinct, that's very interesting for us.
Yeah, are you also looking at airborne systems for measuring surface currents?
We would like to, but we haven't been doing that. We've been using airborne systems, for example, here in Porto, then again, in cooperation with José da Silva and other people from here, to basically study the plume of the Douro River. So the way it goes into the ocean or so, because you can spot it from let's say, space, using then again SAR imagery when conditions are right. But we also use that to basically get a good sense for where the front is, so that then we can sample with the AUVs. So we have AUVs, the kind of performing the kind of front tracking algorithms to basically characterize the plume of the Douro River. And we've got some interesting and at the same time surprising results.
Okay, brilliant. Thanks.
For example, because you mentioned internal wave, just a brief comment, which is in one of our first surveys, we noticed that the thermal line was, let's say, pretty stable, normal, and then in another run there was a dip in the thermal line, and we don't have enough data to basically say much about that, but that kind of looked interesting.
Yeah. Okay, I also need to make a big effort to be brief when it comes to internal waves. So I thank you again for a very interesting presentation, and for keeping to time well, both of you. And thanks again for Martin to both of our speakers. I thank you very much for your contributions towards this online conference. Hopefully we'll all get some feedback sometime, and that somebody will watch this and found it useful. I've certainly enjoyed it, and I thank you also to the organisers who've done a great job of keeping this conference going under these circumstances, and all the efforts they're making to record these sessions now. I'm sure that they'll be looking forward to that job being done and done well, and I hope everybody makes the time and effort to engage with the conference and participate as much as possible. And we look forward to meeting face to face again in the not too distant future. In the meantime, stay very safe, and thank you, everybody.
Yeah, thank you.
Goodbye for now.
Bye, stay safe.
Bye-bye.
Bye.